Hi everyone, welcome back to Chem Help ASAP. It is Wednesday, which means it is time for a new live stream. So last week we did do some Lewis structures, but we didn't do any expanded octet Lewis structures. Oh good, thank you OG Benchmark, said audio is good. So I thought this week we would do some more Lewis structures, but we would work with the expanded octet Lewis structures. And then once we're finished with that, let's talk about molecular geometry. And specifically, we're going to talk about molecular geometry using VSEPR theory. Now that's valence shell electron pair repulsion theory. So let's go ahead and jump into our expanded octets. Okay, so just like we did last week, I'm putting the rules for Lewis structures up here. We are going to still follow these rules, even though, yes, I am spoiling everything. These are going to be expanded octet because we are still following this rule, except I will show you where to expand that octet because that is rather key. So we're still going to add up the valence electrons, sketch out arrangement of the atoms, and then start sharing electrons between atoms, just like we did last week. Okay, so let's go ahead and jump in to our first structure with an expanded octet. Now, looking at this molecular formula, SF4, you wouldn't necessarily know immediately that it is expanded octet, but I'm going to show you how you identify that. And it's not until you get into the structure that you're going to know it's expanded octet. So this is not something that you're going to look at the molecular formula and say, oh, yes, this is going to be expanded octet. Some of them will be very obvious, but some of them you won't know until you get started. So that's not something you have to determine first before you start your first step with the Lewis structure. All right, so we're going to start with step one. We're going to add up our valence electrons. So sulfur gives us 6 valence electrons. We have 4 fluorines. They each give us 7. That is 34 valence electrons. I'll put a little E under here. So that is how many electrons, again, we put in our pot for everybody to share. Okay, so that is step one. Step two is we're going to sketch out an arrangement of the atoms. Again, this is our first best guess as to what the structure might be. You can always change this up. Again, this is your first best guess. Now, what I want to do is I want to identify the central atom, and sulfur is written first, and it is alone. There's only one sulfur atom, so that is my central atom. So I'm going to put, I've got lots of space here, I'm going to put sulfur, and then I'm going to put my 4 fluorines just around sulfur. And you can put them however you want to put them. I tend to go top, bottom, and left, right, but you don't have to do that. They just have to go around the central atom. So what this avoids is drawing a structure that is S, F, 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 F. Right. So then you're stuck with a linear arrangement, and you also are gonna have a tough time satisfying octets here. So remember, when you're doing these Lewis structures, the key is to find the central atom and then put everything else around it. Okay, so I'm going to erase this because that really bothers me. We're just not gonna even keep that up. Okay, so that is my first step for Lewis, my second step for Lewis, and my third step is we're just going to start putting electrons in, but of course it's best, I think, to start with single bonds everywhere. So I know that this sulfur must be bonded at least with a single bond to all 4 of these fluorine atoms because they share a covalent bond. So now I'm going to just start counting things up here. So I have used 2, 4, 6, 8 electrons. So now I'm just going to add in electrons until I run out there. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so I have used 32 electrons, but I have maxed out everybody's octet, but let's double check. So I'm just going to write a little note to myself. 32 electrons used. I have 34, so I cannot just destroy electrons out of nowhere. I need to make sure that I use 34, but at this point, I think everybody has 8 electrons, so let's see. Okay, so starting with my sulfur, if I were to draw a circle around here, I have 2, 4, 6, 8 electrons, so sulfur's octet is satisfied. Fluorine here has 2, 4, 6, 8. Yes. And you can see that all of these fluorines are single bonds with 3 lone pairs. So these are all going to be full octets. These are going to be satisfied. So I have satisfied all octets, but I have a problem. I've only used 32 electrons and I need to use 34. This is when you know you need to do an expanded octet. So the question is, where do you expand the octet? The answer is you're going to expand the octet on the central atom. And in this case specifically, so if you find sulfur on the periodic table, so sulfur is atomic number 16, you will find it is in the 3rd period or the 3rd row. That means it can take an expanded octet. If you are in the 2nd period or the 2nd row, or if you're hydrogen or helium, you cannot have an expanded octet because you do not have access to d orbitals. But remember, when you do electron configuration, the first d orbitals are 3d orbitals, which means if you are in the 3rd period, you have access to those 3d orbitals, which means you can have an expanded octet. So just to be really clear, if you're dealing with a molecule and carbon is your central atom, you will never have an expanded octet on carbon or oxygen or nitrogen. It simply is not a big enough atom to take those extra electrons. Okay, so let's deal with these extra, because we still haven't dealt with these extra electrons. So I just have 2 extra electrons or 1 pair of electrons. I'm going to put this on the central atom, and I'm going to put them right here. So what does this do to sulfur? So if I count up my electrons for sulfur now, I have 2, 4, 6, 8, 10. So sulfur has 10 electrons. Again, it is an expanded octet because it's more than 8. Okay, let's make sure no questions. We're going to do some more of these. We're going to do a good bit more of these because this takes a while. It takes practice. Okay, so we've got 2 here. Let's start with our xenon tetrafluoride, or XeF4. Again, I'm still following my rules, my 1, 2, 3 rules for Lewis structures. I am going to add up the valence electrons. So xenon has 8 valence electrons. Yes, it's a noble gas. It does do some bonding. And then I have 4 fluorines. So this is going to be 36 valence electrons total that I have to work with. All right, so that is step 1 done. Step 2 is I'm going to sketch out my arrangement of atoms. So I want to identify my central atom. Xenon is written first, and there's only 1 xenon atom. So I'm going to guess that that is my central atom. So I'm going to put xenon here. And again, I'm just going to put my 4 fluorine atoms around like so. Okay, so that is step 2. Step 3 is I'm going to start by sharing 1 pair of electrons. All right, so we have single bonds in between xenon and each fluorine. I know that must be the case. So I have used 8 electrons. Just like before, I'm going to start adding electrons in until I feel like maybe I've satisfied octets everywhere. Okay, so this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So once again, I have used 32 electrons, but I need to use 36. So this time I have 4 extra electrons, but just like last time, I'm going to put my extra electrons, or you can think of them as your extra pairs of electron, on the central atom. Xenon is in the 5th period, so it's certainly large enough to take the extra electrons. It can have an expanded octet, so I am going to expand its octet. Let's see, I've got to put 2 pairs in, so I'm going to put 1 on this side and 1 on that side. So now I have used all 36 electrons. So what is hard about this, or difficult, and students make mistakes, is once all the octets are filled, then they just stop adding electrons. Well, once you've added up your valence electrons, that is the number that you have to be committed to, whether you need to make atoms share more, or in this case, you need to expand octets. So we cannot create more electrons, and we cannot destroy electrons that we don't want to use. We must use the total number of valence electrons. So let's check our octets here. So you can see a fluorine, 2, 4, 6, 8, and all fluorines are going to be the same like this. They're going to have 1 bond, and they're going to have 3 non-bonding or 3 lone pairs. That's 8 electrons. But if I look at xenon, of course it has the 8 electrons here from the bonds, but it now has 4 more. So it has 12 electrons. So it has an expanded octet. Okay. Oh, hi, Jessica again. No, that's no problem that you're late. Can you please explain? Oh, about the expanded octet. So the rule about the expanded octet is you have to be in the 3rd period or lower. So the 3rd row or lower, because if you think about your first set of d orbitals when you do your electron configurations, those are the 3d orbitals. So once you hit the 3rd period, those elements have access to those extra orbitals, that extra space to put electrons. And if you are in the 2nd period, or if you're hydrogen or helium, you don't have any more orbitals. So I said before, if you are, say, carbon, nitrogen, oxygen, fluorine even, you don't have enough space to have more than 8. So you will never see carbon with 10 electrons around it, or if you do, it's wrong. So those 2nd period elements, they just can't take any more. So if you're going to expand an octet, you want to make sure that it is 3rd period, or either you can think of it either lower on the periodic table or a higher period number. So if I'm looking at this xenon tetrafluoride and say I was tempted to expand the octet on one of these fluorine atoms, if you find fluorine, and fluorine is atomic number 9, you can see it's in that 2nd period. It can't take any more. Like 8 is its max, and it's not going to do any more than that. So I hope that explains when you use expanded octet and when you don't. But also the rules for Lewis structures for expanded octet is you're always going to add these extra electrons to the central atom. Now, if you find that your central atom is in the 2nd period, like maybe your central atom is carbon, then something has gone horribly wrong. And I would first go back and double check your count of valence electrons, and then double check your count of how many electrons you have used. Because that's, I made the mistake last week. I just added up my valence electrons wrong. It happens all the time. So those are the places to double check. Again, if you end up with a structure where you really want to give carbon 10 electrons, because don't do that. Poor carbon, it can't take that. Okay, so that is xenon tetrafluoride. Let's go on to our next one. This would be iodine trichloride, or ICl3. Let's go ahead and do the Lewis structure for this. Again, I'm going to follow 1, 2, 3 rules, and just like you already know, yes, there's going to be an expanded octet here. So let's count up valence electrons. Iodine gives me 7. I have 3 chlorines, which also give me 7. So I have 28 total valence electrons in my basket. Identify my central atom so I can sketch out my arrangement. Iodine is written first. It's all by itself. I'm going to put that in the middle. So we'll put iodine in the middle, and I'm going to put my 3 chlorine atoms around iodine. Again, it doesn't matter how you put them around. Don't worry about bond angles or trying to determine the shape yet. You just want to get those chlorine atoms around. Okay. So now that I have my best guess as to what the arrangement is, I'm going to start by sharing 1 pair of electrons. So I'm going to do single bonds between this iodine and those 3 chlorine atoms. So I have used 6 electrons. So I'm just going to start adding electrons in to try and satisfy everybody's octet. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, but I've got 28. Okay, so I'm just going to give myself a note. 26 have been used so far, but I need to do 28. So let's check and make sure everybody's octet is filled first before I start expanding. All right, so if I look at iodine, my central atom, I have 2, 4, 6, 8 electrons. Okay, great. If I look at chlorine, I have 2, 4, 6, 8, and you can see these other chlorines are the same. Single bond, 3 lone pairs, single bond, 3 lone pairs. So everybody's octet is already satisfied, which means I can start expanding. Now, this is a situation where a chlorine and iodine can both take an expanded octet. So where do you expand the octet? You're going to expand it on the central atom. So I have one more pair of electrons to use. And, you know, I'm just going to make a little bit of extra space here. So instead of iodine having 1 lone pair, it is now going to have 2 lone pairs. Now, you don't have to draw the lone pairs like I did it. I just wanted to make it clear that there were 2 lone pairs. You can put them over here or over here. It really doesn't matter, just so it's clear that iodine now, instead of having 8 electrons around it, has 2, 4, 6, 8, 10 electrons. It's got an expanded octet. Okay, hopefully these are clear. Good, I'm not seeing any more questions. So we're gonna keep going. We're gonna keep practicing these guys, because I think seeing it several times over is when it really starts to cement in your head, because the first couple of times you're going, wait, what? So now we have xenon dichloride. So we'll do this one first. Again, following our rules, I'm going to add up my valence electrons. So xenon has 8, and I have 2 chlorine. They each have 7, 22 electrons. Okay, so again, doing my arrangement, I'm going to put xenon in the middle because it's written first and it's all alone. And I just have 2 chlorine, so here we go. Chlorine 1 on each side, but again, do it however you want. Okay, so step 3, I'm going to start with single bonds. So I know I have to have at least a single bond there between these two. So I have used 4 electrons. So this is 2, 4, 6, 8, 10. Okay, that electron is really janky. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and at this point it's looking like everybody's octet is satisfied, but I have not used all of my electrons, so let's just double check octets at this point. So xenon here has 2, 4, 6, 8, okay, so satisfied octet. Chlorine has 2, 4, 6, 8, and again, this chlorine is the exact same. So you also might be noticing a pattern, especially with the halogens, that they tend to, especially if they're not a central atom, they tend to form single bonds in 3 lone pairs. That's just something you commonly see. Okay, but I have an extra pair of electrons that I need to put in. So where do I put it in? I'm going to put it in on the central atom because that is the octet that I'm going to expand. And I'm just going to make a little space on the top here. So xenon is going to have 3 lone pairs around it instead of just 2 lone pairs. And now let's double check, make sure I've used 22 electrons. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, yes, I have used all of my 22 electrons because again, I can't just drop 2 electrons because I decide that they are no longer valid for some reason. We have to use our number of valence electrons. Moving on, we're still doing more examples. So let's do phosphorus pentachloride. Okay, so same rules, counting up valence electrons first. Phosphorus gives us 5 valence electrons. I have 5 chlorine atoms, so that is 7. So that's going to give me 40 electrons. Yes, okay. I'm always just double checking my math because you never know when things are going to go sideways. Central atom is going to be phosphorus. It's written first. It's all alone. So I'm going to put phosphorus. Now this time I can tell from the molecular formula I have to have an expanded octet. If phosphorus is bonded to 5 atoms, even with single bonds, that's going to be 10 electrons. This is going to have an expanded octet. The question now for me is, how expanded is it? Okay, so I've got to fit 5 chlorine atoms around here. 3, 4, 5. Again, just put them around however it makes the most sense to you. And now I'm going to share 1 pair with everybody at least. Okay, so we're going to do single bonds. I know this feels kind of weird, or it feels a little bit weird to me to put 5 bonds around phosphorus, but it's got to be bonded to each of these chlorine atoms. So that is 10 electrons. I'm just going to start putting them in. I'm going to start counting. Okay, so that's 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, so I have used all of my electrons, so it looks like I'm not having any left over, but again, it's still an expanded octet because how many electrons around phosphorus? 2, 4, 6, 8, 10. So this is a case of an expanded octet that's taking more bonding electrons instead of adding in extra pairs of non-bonding electrons. And you see both. Or before we go on, let's just double check our chlorine. So you can see a single bond, 3 lone pairs. That's going to be 8 electrons around all of these guys right here. Yep, and that one has 8 as well. So you do want to make sure that all of your atoms have 8 electrons before you start expanding into it. But this one is PCl5. If the phosphorus is bonded to 5 atoms, automatically it has an expanded octet. Okay, so Jessica, when would you use double bonds? Yes, so we're kind of going the opposite way of double bonds here with expanded octets, but when you're doing Lewis structures, again, I always like to start with the single bonds. Start with your single bonds. I just start adding electrons in, trying to satisfy all octets with either a single bond and then whatever electrons I have left over. But when you have a double bond or a triple bond, what you'll find is you run out of electrons before octets are satisfied. So in these expanded octet cases, I'm going the opposite way. I'm satisfying everybody's octets and I've got electrons left over. I've got too many to deal with. But when you have double bonds and triple bonds, what you'll find is you put all the electrons in and you've got some atoms that maybe only have 4 electrons around it or only have 6 electrons. So when you run into that, what you want to do is you want to make the atoms share more electrons. So instead of just sharing 2 electrons with a single bond, bump that up to a double bond. Make them share 4 electrons instead of 2, or make them share 6 electrons. That would be a triple bond. So this is again why I like to start with single bonds, because I feel like it gives me both avenues. Am I going to need to do an expanded octet because now I've got a lot more electrons than I know what to do with? Or do I need to see that some of these octets are not satisfied and I need to make them share more? And I tend to go systematically. So I start with single bonds, and if that doesn't work and I need to share more, then I go to a double bond first. And then if I need to, I go to a triple bond. So I try not to jump around a lot because for me, it just disorganizes my thoughts and I'm not sure what I've tried and what I haven't tried. So I tend to go single bond, double bond, and then triple bond if I need to. So hopefully that helps answer that question there. But again, all of these, it's just about practice, which is why I like to do lots and lots of examples. Like, see what these look like, and you'll start to pick up patterns. Like with all of these halogens having a single bond and 3 lone pairs, you see that all over the place. So, I like to work lots and lots of examples. Okay, great questions, by the way. I love the questions. Okay, we've got, let's see, I think these are my last 2 examples of the expanded octet, and then I definitely want to talk about our molecular geometry as well, because you have to have your Lewis structure before you do molecular geometry. But anyway, let's still focus in on our Lewis structures here. All right, so let's do this iodine pentachloride. Again, you can tell this one has got to have an expanded octet because I have to have that iodine bonded to 5 atoms. That's automatically going to be 10, but we just need to, again, count up our electrons and figure out how much that octet needs to be expanded. So let's count up valence electrons. Iodine gives me 7. I have 5 chlorines. So I have 42. Always double checking that mental math, right? Okay, iodine is going to be central, so I'm going to put it in the middle, and again, I'm going to try to put 5 chlorine atoms around this fairly neatly. That's 4. Okay, I can fit 1 more in there. All right, so there's my first best guess with my central atom and my 5 chlorines around. So now I'm going to start with single bonds everywhere. So again, after I put these single bonds in, you can see that iodine already has 10 electrons, but that's okay because if you look at your periodic table and you find iodine's atomic number 53, it's past the 3rd period. It can take an expanded octet. That's not a problem. Okay, so I've used 10 electrons. Let's put some electrons in and let's see if we need to expand this octet anymore or if we're good. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, but I've got to use 42. Okay, so I need to make myself a note. I have used 40 electrons. I still have 1 more pair, but before I slap that pair on that iodine, let's just make sure that octets are satisfied. So again, I've got my halogens with my single bond and my 3 lone pairs. So 8 electrons, 8 electrons, 8 electrons, 8 electrons, 8 electrons. So octets are satisfied. Iodine already has 10, so it's already passed. So again, for this extra pair of electrons, I'm going to put it on my central atom. And so there, I just try to find a good space for it, maybe right here on top. Put it wherever it works for you on your structure, just so it's clear that iodine has 5 single bonds and it has a lone pair. Okay, so we've got 1 more here, and then we're going to do molecular geometry. And we're actually, assuming I've got enough time, I want to do molecular geometry not only on just the Lewis structures with octets, but also the Lewis structures with expanded octets. Okay, so let's get this one last Lewis structure drawn, and then we'll move on to VSEPR. Okay, so adding up valence electrons. So selenium 6. We've got 6 chlorines. Those each have 7. 48 valence electrons. That's a lot of electrons. Okay. Selenium is going to be central. And now I've got to fit 6 electrons around here. Sorry, 6 electrons, 6 chlorine atoms. 3, 4, 5. Okay, yes, that is 6 chlorine atoms around there. I already know selenium has got to have an expanded octet. And again, check, selenium is atomic number 34. It is in the 4th period, so it can have an expanded octet. That's fine. Let's put in our single bonds. 6 single bonds around selenium. So definitely selenium has hit 8 electrons. Let's start adding electrons in. So this time I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, okay, 48. So I have actually hit my limit of electrons. It's funny when you see students doing Lewis structures, you hear all this counting like under everybody's breath. I mean, I still do it too. Like I need to count and keep track of all the electrons. All right, so selenium. Selenium, good old selenium. It has taken 12 electrons, and that's fine. It can handle it, so definitely octet satisfied. And again, for all of these chlorines, you can see it's the same pattern. We've got a single bond, and we've got 3 lone pairs, and we do this for all of them. So yes, all of these octets are satisfied, and we have used our 48 electrons. So this is the Lewis structure for selenium hexafluoride, just to use my naming rules correctly. Okay, any other? Okay, so we've got some more questions. Okay, hold on, let me catch up here. Oh, the static was coming back. I'm wondering if my headset is said, yes, that's my cat. I didn't know that you guys could hear. Yes. So our poor little kitty cat, she's 17 years old and she's deaf. So I think she tries to hear herself meow, and she meows very, very loudly. Oh yes, OG benchmark. Yes, she does cry in the hallway. I know, poor baby. But otherwise, like she's healthy. I just took her to the vet. She's fine. She eats her food. She drinks her water. But she just, yes, I think she tries to hear herself meow. Sometimes at 2 o'clock in the morning, that's not such a great thing to hear. Okay, let's go on to VSEPR. And yes, you might hear our cat in the background again. You know, yes, I do have the door closed behind me, but she also likes to, of course, jump up in my lap and interrupt me when I'm doing things like this. Okay, so VSEPR, again, this is one way that we predict molecular geometry. It stands for valence shell electron pair repulsion theory. And again, it's a way we can predict bond angles, because when we draw Lewis structures, again, we pick a central atom and we just put atoms, the other atoms around that central atom. And we're not worried about, oh, is that a 90-degree angle? Is that 180? Is that 120? Because we just want to get the electrons in the right place. So this is really an application of Lewis structures, because you have to draw your Lewis structure first, and then you can predict the molecular shape. So I am going to draw the Lewis structure for these compounds, but I'm going to draw it pretty fast just because I want to focus on the shape of the molecule and how we predict the shape from the Lewis structure. But I believe all of these examples that I'm getting ready to do, we did the Lewis structures last week. So if you want to see me run through with the 3 steps of how to do the Lewis structures, that is on the live stream for last week. And like I said, if I'm remembering correctly, I did do all of these Lewis structures. So I'm just going to jump in here for methane CH4 and just draw the Lewis structure. So this is going to be carbon with 4 single bonds to hydrogen. Okay, so there is our valid Lewis structure. Now let's use that Lewis structure and let's predict the molecular shape. So you see I've got my little table here with all my pretty pictures. So what we do first is really I focus on this second and third column. So the first thing I want to do is I want to take a look at the central atom, and I want to count how many atoms are bonded to that central atom. So I'm not counting bonds, I'm counting atoms. So carbon is my central atom. So I'm just counting how many atoms are bonded to carbon. And I have 1, 2, 3, 4 atoms bonded to carbon. Again, it doesn't matter if they're bonded with a single bond, a double bond, or a triple bond, because I'm counting atoms, not number of bonds. And that's something that students find tricky. Okay, so this carbon atom is bonded to 4 atoms. So if I look down this column, I'm looking for a 4, and here's a 4 right here. And there's actually only one option, but we will confirm with the next column. So I'm looking for non-bonding pairs next, and I'm hoping that there are 0, because if this works, there should be 0. So again, looking at the central atom. So these are not, and you know what I'm going to do, because I've been calling these lone pairs. I'm going to mark that out, and I'm going to call this lone pairs here. Lone pairs, non-bonding pairs, they're used interchangeably. They mean the same thing. I find that different times I get kind of in a habit of using one or the other. So again, if I'm looking at carbon, you can see there are no lone pairs on carbon, which again, 4, 0. So this molecule is tetrahedral. And so it's going to look like this in 3 dimensions. So we draw it flat as if there are 90 degrees here between each hydrogen atom, but that is not the case. It's got a 3D structure where really you can think of it as like this hydrogen is coming out of the plane a little bit. These two are going back kind of behind the page there. And you could consider this hydrogen maybe within the page. So this has a 3D structure. We have to be able to draw it on a 2D page or like a 2D screen. So let me go ahead and label this. This is tetrahedral. Okay, let's go ahead and go on to ammonia, or NH3. Again, I am just going to pop the Lewis structure on here instead of going through all the steps because I want to focus on molecular geometry. Okay, so here's our Lewis structure for ammonia. I'm going to do the same thing. So first, I'm going to take a look at the central atom, and I'm just going to count how many atoms are bonded to the central atoms, not bonds, just atoms. So I have 1, 2, 3 atoms bonded to my nitrogen. So I'm looking for 3s here. So I've got a 3 here and I've got a 3 here. So I've got a couple possibilities. So I need to narrow this down, and I narrow that down by looking at lone pairs. So again, focusing on just my central atom, not lone pairs anywhere else, just central atom. Looking at nitrogen, I have 1 lone pair. So that means it is not this guy, but I have 1 lone pair, so I am trigonal pyramidal. Let me just write that down here. Trigonal pyramidal. So the shape is what it sounds like. It's going to look like a pyramid with a triangle base. So you can see kind of here's a better 3D structure than what I can draw. But again, if I'm just drawing the Lewis structure like this, it looks like there should be 90 degrees, but the way you draw the Lewis structure may or may not be how it actually is in 3D. This is why we do the Lewis structure first, and then we apply, in this case, our VSEPR theory to determine what the 3D structure is. Okay, let's go on. We're going to do some more examples because I want to do expanded octet. Turn the page. Thank you. All right, so now I have my nitrate anion. Again, I'm just going to throw the Lewis structure up here. If you want to see how to do the Lewis structure, check out the live stream from last week. So nitrogen is my central atom. I've got this, and these guys have lone pairs. Here we go, and this one has 2, and this whole structure does have a charge of -1. All right, so here is my Lewis structure for my nitrate polyatomic ion. Now let's determine shape. This is where it's really important to be counting atoms. So the first thing I want to do is I want to know how many atoms are bonded to my nitrogen here as a central atom. And this is where it's tempting to see this double bond and count that as 2, but we're not counting bonds, we're counting atoms. So I have 1, 2, 3 oxygen atoms bonded to that nitrogen. So again, I'm looking for a 3 here, so I've got 2 possibilities. So now next I need to look for lone pairs. Let me change this again. We're calling these lone pairs for this live stream. So again, I'm looking at my central atom. So I'm not checking out lone pairs on any of the oxygens. They are not the central atom in this case. I'm just looking at my nitrogen as a central atom, and there are no lone pairs. So that means I'm not trigonal pyramidal. I am trigonal planar. So close, but not the same thing. So this one you could draw more easily in the plane, but again, you wouldn't have 90-degree angles. You would maybe angle these oxygens maybe up a little bit more and make it look more like a triangle with 120 degrees between these. But again, when we do the Lewis structure, don't worry about trying to predict bond angles. Get the Lewis structure first, then predict your molecular geometry. Okay. Just making sure there are no questions. We're going on to sulfur dioxide. So this one looks like this. I think maybe in the live stream last week we maybe did ozone, O3 for this, which is very, very similar. Again, if you can't find how to do the Lewis structure for any of these and you have a question, always just leave me a comment even after the live stream is done, and I'm happy to answer any of those questions. Okay, so sulfur dioxide, again, we want to predict shape, and let me erase all my X's here because I might need this structure. All right, now I've got a clear table. So again, always focusing on my central atom. So here is my sulfur. It's in the center. I want to know how many atoms we're bonded to. I am bonded to 2 atoms. Again, it's so tempting. I see this all the time that students want to count that as 2. It doesn't matter. You're just counting atoms. Okay, so I'm looking for 2. So I can be 2 atoms. I've got 3 different options to choose from. So now again, I want to look at lone pairs on my central atom. So I'm making sure I'm looking at central. I'm not looking at these guys. I'm looking at central, and I have 1 lone pair. So here I am bent. So not this and not that one. So this is bent. Okay, any questions about this before I move on? Okay. I haven't heard my cat recently, so maybe she is satisfied with kind of hearing herself meow. Anyway, okay, so a couple more shapes here, and then we're going to go on to those expanded octet shapes, because that's a whole nother table with a whole nother set of shapes. But let's do these first. All right, so carbon dioxide. So this one's got 2 double bonds, like this. So let's determine shape. Checking out my carbon, focusing on my central atom. Carbon is bonded to 2 oxygens. All right, so I have a lot of possibilities where I'm bonded to 2, where my central atom is bonded to 2 atoms. So now I'm going for lone pairs. Again, lone pairs on my central atom, and carbon's got no lone pairs, it's got nothing. So I am going to be linear, not this one and not that one. Here we go. Carbon dioxide is linear. So, if you drew it like this, you'd actually be drawing the bond angles right. But it doesn't matter. You could draw that at a 90-degree angle and you'd still have a valid Lewis structure. You just would maybe want to redraw it if you're trying to draw it how it is in 3D space. Okay. I wanted to erase my X's for my next example. But when I'm doing these, I do like to cross out the possibilities that I know are not true, especially when I have 2 atoms bonded to the central atom, because again, it's very tempting and it's very easy to accidentally pick the wrong shape. So give yourself as much help as you can. All right, so now we've got water. Now water is interesting because we do write it H2O, but in this case, oxygen is the central atom. So it's not written first. Okay, so it maybe should be, but we've just always written water H2O. But oxygen is also an atom that is alone. So that, in this case, that's how you would know that for water, oxygen is your central atom. Okay, so here is the Lewis structure for water. So let's determine the shape. So my oxygen is bonded to 2 hydrogen. Okay, so again, I've got 2, so any of these possibilities. Let's do lone pairs. Again, on the central atom, I have, in this time, I've got 2 lone pairs. So not this one, not this one, it's going to be this one. So again, this is, you notice there are 2 options for bent. So water is also bent. And so the Lewis structure here, again, is valid. It's fine to draw it this way when you're looking for a valid Lewis structure, but just know that in 3D space, it looks a little bit more like this. So if you really wanted to, you could draw it with these hydrogens kind of pointing down, and then you put the 2 lone pairs on oxygen like this. But again, both of these, totally valid Lewis structures. Okay, good, no questions. So hopefully these were easy. Let's do our expanded octet. So for our expanded octet and our molecular geometry, see, we've got a lot more shapes to choose from. These are the Lewis structures that we did at the beginning of the live stream. And I specifically wanted to do that because then I can just write down the Lewis structures just from the get-go, and you've already seen where they come from. So SF4, this is the one that had the lone pair or the non-bonding pair on the sulfur right here. And of course, all of these fluorines have all of their lone pairs. Okay, give me just a second. These expanded octet structures just have lone pairs all over the place. Okay. Okay, some of those electrons are a little bit wild, but hopefully you understand what I'm drawing here. All right. So SF4, let's predict molecular geometry. We do it the exact same way. We really focus in on that central atom. So I'm focusing in on sulfur. So the first thing I want to count is how many atoms are bonded to sulfur. And I have 1, 2, 3, 4 atoms. So I'm looking for 4s. It could be this one or it could be this one. Okay, so next I am looking for lone pairs on that central atom. So again, if I'm looking at sulfur, I have 1 lone pair, which means, yeah, I'm this one, I am not this one. So this structure is seesaw. And if you, that W went kind of crazy there. Seesaw. Again, if you look at the 3D shape right here, it kind of looks like you could maybe sit on these ends and it would teeter-totter back and forth. I don't know. I didn't come up with the shapes. This is just what I see. Okay, so that is a seesaw shape for SF4. Let's go on to xenon tetrafluoride. This Lewis structure had, of course, xenon in the center, 4 fluorines, and then that xenon ended up with 2 lone pairs, like so. All right, that's my central atom. Let me go in and put all of my lone pairs for all of my fluorines. Again, these halogens very often, not always, but very often end up with single bonds and 3 lone pairs. Almost there. Okay, there we go. So looking at my central atom, but let me erase my marks here. Okay, we've got xenon. How many atoms is it bonded to? 1, 2, 3, 4. So bonded to 4 atoms. This guy and this guy. Let's find lone pairs on my central. I've got 2 lone pairs. All right, not this one, that's X. It's going to be this one, so this is square planar. And so you can see with this one, what it does is these yellow balls here are their lone pair. So the lone pair goes kind of on top and on bottom, and those 4 fluorine atoms form the square plane there. So it's, I think it's pretty cool. Okay, let's keep going through again. Yeah, we've got time. We're going to go through all of the ones that we did Lewis structures for expanded octet. So ICl3, this one, of course, was bonded to 3 chlorine atoms, and it had 2 lone pairs on the central atom as extra. And let's put these lone pairs around the chlorine. So you can see iodine is the central atom here. It is a halogen, but it does not have that single bond and 3 lone pairs. So that's why I say with the halogens, you often find them with a single bond and 3 lone pairs, but not always. All right, so focusing on our iodine, because it's the central atom, I am bonded to 1, 2, 3 atoms. So it could be this guy. It looks like it can only be this guy, so let's double check our lone pairs. So again, on my central atom, I have 1, 2 lone pairs. Okay, this is matching up. It's always nice when you get confirmation that yes, you have chosen the right shape, and it just confirms too that your Lewis structure is correct. So if you ended up with 3 atoms bonded to the central atom and maybe you only had 1 lone pair, then you would go, wait, something is wrong because that's not a possibility. So it's always nice when everything lines up and you're going, okay, this is the right answer. All right, so now we have xenon dichloride. This was xenon, of course, bonded to 2 chlorine atoms. I think it had 3 lone pairs around it. So there are the 3 lone pairs. And let's make sure we give chlorine all of its lone pairs here. There we go. There we go. Okay, so checking out xenon, our central atom. It is bonded to 2 chlorine atoms. Oops, let me erase this. Start fresh. So I'm bonded to 2 atoms. Okay, so I'm really hoping that this works out, right? Okay, so looking at my central atom, I have 1, 2, 3 lone pairs, which, yes, is exactly right there. So this is linear. So it's the same shape as carbon dioxide, although obviously very different atoms and way different lone pairs. But if you look at the 3D shape here, you can see the lone pairs. Again, it's these yellow balls arrange themselves in the center, and they pop those 2 chlorines out on either end. Okay. Doesn't look like there are any questions, so we're just going to keep on trekking here with our other structures. So we just have a couple more structures. So we did this PCl5. Again, this is phosphorus bonded to 5 chlorines. 3, 4, 5. And give me a minute. Let me put in what feels like 100 lone pairs. But they need to go in because we need to know where they are, and we also need to confirm that everybody's octet is satisfied. And with this one, there were no extra lone pairs on the phosphorus in the middle. Okay, so central atom, phosphorus, how many atoms is it bonded to? 1, 2, 3, 4, 5. So I can be this guy, or I can be this one down here. Okay, so let's take a look again at our phosphorus. I have no lone pairs, no non-bonding pairs. So it's not this one. It's going to be this guy. So this one is trigonal, bipyramidal. So that's really kind of an interesting shape there with the pyramid with one on top and one on bottom. Again, when we draw the Lewis structure, just put your chlorines around so you can have them organized in your head and you know where they are. Okay, next we have our ICl5. This one was very similar because we have the 5 chlorines around. But I believe this one had an extra lone pair on the iodine. Let me check. Yes. We had an extra lone pair, so I'm going to just put that here. And of course, give me a minute to get all of these electrons around chlorine. Oh, whoops. And see, I forgot a pair. And I know this takes time and you get tired of doing it, but the last thing you want to have happen is to be on a test and you've gotten lazy about putting all of your lone pairs around your outside atoms and then to get points taken off. So I know it's a pain, it takes some time, but just it's a really good habit to be in. Okay, so our iodine, our central atom. How many atoms is it bonded to? 1, 2, 3, 4, 5. Oops, okay, so it can be that one or it could possibly be this one. But we need to check non-bonding pair. So in this case, iodine has 1 non-bonding pair, so it's not this one. It's going to be this one, so we are square pyramidal. Okay, so we have one more to do. Our last one, our SeCl6. Okay, so I've got to fit 6. 1, 2, 3, 4, 5, 6 chlorines right here. There were no lone pairs on the selenium. I mean, so you guys can probably already decide what shape it is. Well, I put in all of the lone pairs around these chlorines. Okay, we're almost getting there. Almost one more to go. Whew. All right. So selenium, my central atom, is bonded to 1, 2, 3, 4, 5, 6 atoms. Here we go, bonded to 6 atoms. It has 0 lone pairs. Whoops, I didn't switch over. So this is octahedral. And that is our last shape that we have to predict with our expanded octet. So depending on what class you're taking and what level class you're taking, you may just be predicting shape with octets and not doing expanded octets. But I definitely wanted to show both, because certainly by the time you hit college level chemistry, you are dealing with the expanded octets. And if I remember correctly, I think both AP and IB do at least a little bit with expanded octets and have all of these extra shapes to deal with. So as always, please let me know what you want to learn about, or what you're struggling with in class, or even what your next topic is. I am happy to do any chemistry topic in these live streams, so I really want to tailor it to whatever you guys need when we do these live streams. The other thing that I will say, and I'll make sure to put a note on the YouTube channel, is for those of you who are in the US, next week is Thanksgiving for us, so there is no live stream next week. It will resume the week after. So for anybody celebrating Thanksgiving, I am definitely celebrating Thanksgiving and stuffing my face. Happy Thanksgiving, and I hope to see you guys back in 2 weeks. Good night. Bye.